This next section is section 35.4, continuing our work on the chapter on reflection of light and refraction of light in lenses, and we're now going to discuss Snell's law of refraction. It turns out that if we have two different types of media, and let's look at air and we'll look at something else like water, and the velocity of light, or the index of refraction n, is greater in one than the other, then this boundary causes the light to bend as we go from the air to the water. And in fact, the way it bends is going to be more toward the normal. So I'm going to draw the normal here and look at the bending in this direction. You remember that we always use the angle with respect to the normal, so we'd call this an area n1, and this would have an index of refraction n2. This would be theta 1, and this angle here would be theta 2. Now, Snell's law is that n1 times the sine of theta 1 is equal to n2 times the sine of theta 2. And if we look at the index of refractions of, say, air and water, the index of refraction of air is 1, but that of water is about 1.33. Now, since n2 is greater, it implies that the sine of theta is going to be smaller, therefore theta is smaller. And so this angle here is smaller than this angle here. Now, this applies to someone that is looking into water. So if we were to see a fish down here in the water, if you were to look at this fish, it would appear that the fish is actually over here. So the fish is always further away from you, is actually always closer to you than it appears to be. So it appears to be further away at this angle. So if the human eye is up here, looking down here, the light from the fish would go up this way and up this way. Well, whichever way the light goes in one direction, it would also go in another direction. So if you were to send a laser beam down here, it would go along this path and continue along this path. So whether the light is going in this direction or going in this direction, it follows that same path. And if I'm going from something like air to water, the angle is always smaller here, so there's a convergence here. If I actually look at this fish, it would appear to be closer. You can see that if you were to take the fish in the water here and then look at the two lines as they come up here, and it looks like the lines would converge right here, so it would appear to be closer to you than it actually is. Remember Snell's law, because it's used repeatedly and it's the foundation of all of our optics for thin lenses. And this is for light passing from a medium 1 to a medium 2, or in the reverse, relative to the normal. Now let's imagine that we have a lens. These will always be thin lenses, not extremely thick. And if we think of a lens, we can imagine that we would have light here, and the light would go straight across, and it would bend down to an image, and it would go through the center unobstructed. Now that's supposed to be through the center of this lens, and form an image that's over here. So here's the object, and here's the image. This would be a converging lens, and therefore we would say this is the front of the lens and this is the back of the lens, and we can form a real object out here. Draw a line straight through there. But if we were to get this object too close to the lens, then in fact, if the lens looks like this and the object is real close to the lens, then in fact, as the light leaves the object, it can't quite focus. It goes up this way, the light here goes over here, and in fact what happens is it appears that the image is actually from out here. It appears that the image is actually out here. This is to be the object, and this would be the image. It'd be easier if you saw a kind of a nicer diagram that I have from a textbook that shows the light here, where we have a focal length at this point, and they have carefully drawn the light to go down here, to go through the center, and to go through the focal point to down here, where it goes straight over. And that's how we find, by geometry, exactly where this image is. The second one I was drawing was where the object is within the focal length, and then the object, we do not form a real image because the lens is not sufficiently convergent to take this diverging light and bring it into an image that's actually could focus on something. It does bring the lines together, but you can see they're still diverging. And if I retrace these lines, here's one goes here and goes straight over, one goes to the center and is bent down to the focal point, one goes through the center and goes down here. Then, in fact, if I follow all three of these back, you can see that they make an object which is virtual, and therefore could not be focused on an image, on a plane or a surface of any type. So here we have it outside the focal length, here we have it inside the focal length, and that gives you an example. The formulas that are applicable for a converging or a diverging lens, any lens that is sufficiently thin, is given by this formula, the converging lens or diverging lens formulas. And so let me write that out. This would be a focal length. This is the distance to the object. This is the distance to the image, dO for object, dI for image. And the equation that you need to learn is 1 over the distance to the object plus 1 over the distance to the image is always equal to 1 over the focal length. And this is the core equation that we can use for both converging and diverging lenses. Now, if we look at the height of this object, the height of the object, and over here the height of the image, then the ratio of these two is going to give us our magnification. What would the magnification be? Well, we want to know if the image is larger than the object. So therefore, magnification is defined as height of the image divided by height of the object. Now, a little bit of work with similar triangles here using our last diagram can show you that this is minus the distance to the image over the distance to the object. Just by similar triangles, the size of this will be to this as this will be to this. Now, there's some sign conventions here that can be kind of confusing. The focal length is positive for a converging lens and negative for a diverging. That makes sense. D naught is positive if the object is to the left of the lens, it's a real object. And it's negative if it's to the right of a lens, a virtual object. That makes sense also. So we take D naught to be positive if it's there, negative if it's a virtual image. DI, the distance to the image, is for a real image formed to the right of the lens by a real object. And if it's negative, it's to the left of the lens. So automatically, when we solve for DI, if it's positive, we're going to get a real image, and it's going to be on the right-hand side, and it can be for a converging lens. It will always be one that's real and can be formed. But if it's negative, it's going to be to the left. In other words, like the diagram we showed a minute ago, the object would be to the left of the lens if it couldn't converge. The magnification is positive for an image that's upright with respect to the object, and it's negative for an inverted object. and it gives us the degree of magnification by its magnitude. Learn these three conventions, these two equations, and Snell's law of refraction, because they are all very critical.